Hi everyone, we're starting our new chapter on quadratic functions, chapter 17 in your MYP 5 Plus textbook. Now we're going to start looking at section 17a, and we're going to take a look at a couple of examples whereby we're looking at finding the values of y when we're given the values of x, and also finding the values of x when we're given the values of y. So let's do just a couple of examples. It's probably the best way to attack the problem. So if we're given a function and a value of x, we can find its corresponding value of f of x or y. We've done many questions like this where you are told that if you've got f, for example, if f of x equals 2x squared minus 5x plus 10, and you are asked to find f at 2, well, that basically means when x is equal to 2. So wherever there is an x, we are just replacing it with 2. So it would become 2 times 2 squared minus 5 times 2 plus 10, which would go to 4 times 2 is 8 minus 10 plus 10, which ends up giving us simply 8. So what does that tell us? It tells us that when we have a value of x being placed into the function, so when the value of x is equal to 2, the corresponding value of y, so the corresponding value of y, or f of x, remember that f of x and y are the same thing, is going to be 8. And that would actually correspond to a coordinate of that graph of the 2x squared minus 5x plus 10. So that means that the point 2, 8 sits on the graph of 2x squared minus 5x plus 10. Now, if we were given the opposite in this case now, and we were told what the value of y was, and we had to find the corresponding value of x, well, let's take a look at the example that's given. It says find the value or the values of x for which 3x squared minus 3x plus 6 has an f of x value that's equal to 6. So what that means is our value of the y is equal to 6 in this case. Now if that's the case, then that means that our output is 6. Our value of y is 6, and therefore we're trying to find what our original value of x going in was, so that we got an output or a y value of 6. So what we do is we say, well, f of x is equal to 3x squared minus 3x plus 6. Because f of x equals 6, then I can replace that f of x with 6 and make it equal to 3x squared minus 3x plus 6. And now we bring everything over to one side of the equation so that 0 is equal to 3x squared minus 3x plus 6 minus 6. And I've got to... Alright, so now we have 0 is equal to 3x squared minus 3x. We use the null factor law, and we say that 0 is equal to, remove a common factor, 3x bracket x minus 1, so that either 3x equals 0 or x minus 1 equals 0. Therefore, our value of x either equals 0 or our value of x equals 1. So what is this telling us? It's telling us that the two possible values that x is allowed to be, or our input, that will give us an output of 6, or f of x equaling 6, the values could be 0 or 1. Alright. Now, if we wanted to know whether a point satisfied an equation, now what does that mean when we're talking about satisfying an equation? What that simply means is that we want to know if a point is on the graph or on the curve or parabola or whatever our graph is. And all we need to do is replace the point xy in the function, and if the left-hand side equals the right-hand side, then we know that the point is satisfies the function. So for example, here's a type of question that you could encounter. It would be, State whether the following quadratic function is satisfied by the given ordered pair. So what this is saying is, if I am given this quadratic function, if I'm given this curve, is the point -1, -6 sitting on that curve? So what I do is I replace -1 for x, and I replace -6 for y, or f of x. Remember that y and f of x are the same. So that I will write -6 is equal to -7, is equal to -7 times -1 squared plus 9 times -1 plus 10. So that -6 equals, and now I have a -7 minus 9 plus 10, so that we have -6 equaling -16 plus 10, which gives us -6. We have our left-hand side that does equal our right-hand side, and therefore we can say, yes, -1, -6 satisfies the quadratic function. Okay. All right. So the last thing that we took a look at was the investigation. You all worked on an investigation in class that I think is worth our while discussing. All right, so I'm going to briefly go over the investigation so that we can go over everything that that was in the investigation. All right. So let's take a look at the first part of the investigation. So the first part of the investigation dealt with y, or f of x, equaling x squared plus k. Now, x squared plus k meant that we take our x squared function, okay, so we take our x squared function, all right? So I'm just going to do a couple of quick points, 1, 1, 2, 4, and so forth. Okay, there's our y equals x squared function. Now, the moment that I say that I'm going to do y equals x squared, and I'm just going to use a random number, if I say y equals x squared plus, so y equals x squared plus 1, my value of k in this case turns out to be 1. Now, what does the 1 stand for, or this k? It is a vertical translation. Now, we did this already in Chapter 7 when we talked about all the different transformations. So that a vertical translation of k units up, or if it's -1 here, if this had been y equals x squared minus 1, it would have been k units down. And it's still a vertical translation, and this is k units up. Okay, of 1 unit. So let's graph this very quickly. If I do, in the color coding, if I do x squared plus 1, all my points on the x squared graph, the original graph, go up 1 unit. So everything would go up 1 unit, and we would have the graph as such. And that would be my x squared plus 1. I think you can all imagine that if I were to say then x squared minus 1, our original x squared graph would go down 1 unit. So everything goes down by 1. Okay. So that there's my y equals x squared minus 1. And let's not forget to label our graph. And we're going up by 1s here. All right. So when I am looking at when I'm looking at my parabola, the x squared, and I have a plus k or a minus k, that means it's a vertical shift up or down. So that if my value of k is greater than 0, it moves up. And if my value of k is less than 0, it moves down. Okay, so that was the first thing that we looked at in the investigation, in the x squared plus k. All right, the second thing that was observed was when we looked at y is equal to x minus h all squared. And again, if I were to do a quick sketch here, all right, so I'm going to do a very quick sketch. So I have my x, y, and 0, 0, negative 1, 1, 1, 1, 2, and 4, negative 2 and 4. There is my, again, y equals x squared graph. There is my original starting graph. And if I now decide to say, let's do y equals x minus 1 all squared, well, on my calculator, it would mean that my graph is moving 1 unit to the right. So every point gets moved 1 unit to the right. Okay? So that the graph would be right here as y is equal to x minus 1 all squared. And likewise, if I had y was equal to x plus 3, for example, all squared, then my original x squared graph would move 3 units to the left. So it's 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, and right there. So that would be my y equals x plus 3 all squared. All right, now, one thing I did forget to mention in all of these graphs, in both the first and in the second case, is that we have a vertex on all of these, so that the vertex is referring to either the highest or the lowest point. So for example, in the x squared minus 1 graph up here in the first one, in the green graph, the x squared minus 1, my vertex turns out to be 0 and negative 1. My original blue graph of the x squared, the vertex was 0, 0, and my vertex of the x squared plus 1 graph went to 0, 1. If I am looking at the horizontal movement, so when I have x minus h all squared, the second form of the transformations or the translations, this is looking at a horizontal translation. Okay, so we're looking at a horizontal translation. And what the horizontal translation basically tells me is that if my value of the h, if my value of the h is greater than 0, then my graph moves to the right. If my value of the h is less than 0, it moves to the left. Okay, now that might sound like it's the opposite of what I've been telling you all along, but when you think about it, let's take the example of y equals x minus 1 all squared. I'm just going to put that down here. Y is equal to x minus 1 all squared. When I set my y equal to 0 and I want to solve for x, I end up saying I take the square root of both sides so that 0 is equal to x minus 1. And my value of x does actually end up being equal to 1. But notice that it was when it was negative 1 here, but my value of the x is a number bigger than 0, so that when my value of h is bigger than 0, my graph does move to the right, and when my value of h is less than 0, it moves to the left. Okay, and if we're looking at, again, the vertex, well, we can see here that the original graph in blue was 0, 0. The x minus 1 all squared went to 1, 0, the vertex, and the green graph went to negative 3 and 0, its vertex. Okay, now, so that basically covers the two translations, the vertical translation and the horizontal translation. So that, again, recapping, the value of the k in x squared plus k is going to be a vertical shift, moving the graph k units up if k is bigger than 0, or moving the graph k units down if k is less than 0. And we also have that the shape of the graph doesn't change, but the position of the graph does change. Likewise, if we're looking at the horizontal translation, the one underneath, which is x minus h all squared, so when my value of the h is larger than 0, my graph is going to move to the right, h number of units, so it's a horizontal translation or horizontal shift. And when my value of h is less than 0, then it moves to the left, h number of units. Okay, now again, we have no change in the shape of the graph, but there is a change in the position of the graph. Now, the next part of the investigation showed the combination of the two, so that if I had y is equal to bracket x minus h all squared plus k, so the combination of the two graphs basically shows us, that both things can occur at the same time. So let's take an example again, and we'll do one example very quickly, so that I will say there's my x, there's my y, we're going up by ones, and again we're starting with 0, 0, 1, 1, negative 1, 1, 2 and 4, and negative 2 and 4, and there is my y equals x squared graph. Okay, now if I'm going to take now a new graph, I'm going to do a combination of both the horizontal h, so inside the parentheses is my horizontal shift, and outside of the parentheses is my vertical shift. So if I have a graph that is y is equal to x minus 3 all squared plus 4, well, that automatically tells me that my graph is being moved horizontally. It's moving 3 units to the right, and it's going to be moving vertically 4 units up. So I start again with my original y equals x squared graph, and I move horizontally 3 units. So as with my coordinates, or with my with the coordinates that we have, the xy coordinates, I move the 0, 0 point will go 1, 2, 3 units to the right, and 1, 2, 3, 4 units up. So my 0, 0 point, which was my original vertex, is now going to have a new vertex, which is found at 1, 2, 3, 1, 2, 3, 4. It's at 3 and 4. Okay, so you should be able to see at this point that, again, I'm going to move all of the points now, so it's going to be 1, 2, 3, 1, 2, 3, 4, then it'll be 1, 2, 3, 1, 2, 3, 4, and then 1, 2, 3, 1, 2, 3, 4, and then the other one will be over there, and there is my graph. Okay, so it shouldn't be unusual for me to ask at this point, given x minus 3 all squared plus 4, or given y equals, I forgot to put the y, given that y is equal to x minus 3 all squared plus 4, find the vertex of the graph. Well, you should automatically be able to tell me that the vertex of the graph is going to be hk, h being the value inside the parentheses where the x minus or x plus h all squared is, and the k being on the outside, so that I know that my vertex in this problem is going to be 3 and 4. So if I were given if I were given a new graph, such as y is equal to x plus 2 all squared minus 4, and I asked you for the vertex of this graph, then you should be able to tell me automatically, this is my h, this is my k, but remember that when the h comes out of the parentheses, it comes out as the opposite, so it will come out as -2 and -4. That is my new vertex. So this, by the way, is a special form of the quadratic, and it's called the vertex form, because the vertex form, this form is able to tell me what the vertex is every time of my parabola. So again, if I had, for example, 3 bracket x minus 1 all squared plus 5, I know automatically that my vertex is hk, where it's going to be equal to 1 and 5 in this case. There's my h, and there's my k. Alright, so given the general form of y is equal to x minus h all squared plus k, hk is my vertex. Okay, so if it says minus h inside, then it comes out as a positive. If this is a positive h, it comes out as a negative. But the value of the k will always be whatever it is. If it's positive, it stays positive. If it's negative, it comes out negative. Alright, so that takes care of the translations. If we want to just very quickly, I will go over the only other thing that we need to go over, which is the vertical stretches, or the dilations. So let's go very quickly over the vertical dilation. So basically, if I have, again, we're going to have y equals ax squared. The value of the a is your vertical stretch, or it's your vertical dilation, if you want to call it. The value of a will determine what your graph, how your graph is going to look. So your graph, in this case, may not change position, but it will change shape. Okay? So let's take a look at, again, an example. So if I take an example here, such as, again, 0, 0, -1, 1, 1, 1, 2, 4, -2, 4. There's my y equals x squared, and that's like saying 1x squared. So let's do y equals 2x squared. So if I do y equals 2x squared, well, essentially what's going on is that all the y values are being multiplied on the original x squared graph. All the y values are being multiplied by the value of a, which in this case is 2. So 0, 0 will stay where it is, and then 1, 1 will go to 1, 2, because my y value was a 1. 2, 4, so the value 2, 4 on the original graph will go to 2 and 8. So it's 4, 5, 6, 7, 8. And then it's going to be the same on the other side because it's symmetrical. Okay? So that my graph will look something like this. Now, as you can see, the graph has stretched vertically. So what does the rule basically tell us? The rule basically tells us that if your value of the a is going to be greater than 1, or if your value of a is less than -1, your graph gets thinner. It's going to get thinner, and it's going to stretch vertically. It'll become thinner. If your value of the a is between -1 and 1, well, your graph gets wider with respect to obviously, the y equals x squared graph. Okay? Now, the value of the a also determines another thing for us. It determines whether our graph is going to be facing upwards or downwards. So if I have a positive a, so if my a is positive, okay, then that means my graph faces upward. And if my graph is facing upward, that means I have a minimum value here. I don't have a maximum, but I have a minimum value, and my vertex is down here as a minimum. So the minimum is the vertex is a minimum in this case. If my value of the a is negative, well, my graph faces the other direction, because remember that when we have a reflection over the x-axis, all of our y values change their direction. So positive values of y will go to negative values of y. So a negative value of a, so when a is positive, when a is negative, then the graph faces downward, and we have a maximum for the vertex. So the vertex goes to a maximum. Okay, I am just going to do one question that combines everything, and then I'm done. Okay, so if I want to sketch this graph, I've got a combination of everything going here. Okay, so I'm going to make a nice big graph here so we can get a good feel for what it looks like. Alright, and we're going to start graphing the original 0, 0, 1, 1, negative 1, 1, 2, 4, which is on the other side, and negative 2 and 4. Okay, now, I'm going to put the points down in this case. So that we can see everything properly. So the first thing that I would do is I would take care of the vertical stretch, or the value of the a, because my value of the a here equals 3, my value of the h here is equal to 1, and my value of the k here is equal to 2. So I'm going to take care of doing the vertical stretch first. And in the vertical stretch, what that means is that I'm going to start doing it in green. I'm going to do the vertical stretch first, okay, in green. So that means that all my y values are going to get multiplied by 3. So 0, 0 will definitely stay where it is, because 0 times 3 just gives me 0. And then 1, 1 will go to 1 and 3. So there's that point. And then there's the other point on the other side symmetrically. And 2, 4 will go to 2 and 12. So 4, 5, 6, 7, 8, 9, 10, 11, 12, which is there. And then symmetrically on the other side, it will go over there. So there is my graph for, let me just point out that this is my graph for the y equals 3x squared. So there is a vertical stretch. There's the vertical stretch, okay, of the original x squared graph. All right, once I know that my graph is now stretched vertically, what it needs to do, what needs to be done now is the horizontal and vertical translation. And I will do those simultaneously in red. Okay, so the actual translation then is going to be HK, and the HK is going to be 1 and 2, which means that my new vertex is going to be found at the point 1 and 2. So every point on the green graph is going to move 1 over to the right and 2 up. So 1 to the right and 2 up, 1 to the right, 2 up, and then 1 to the right and 2 up. And the same thing over here, 1 to the right and 2 up, and then 1 to the right and 2 up. So that my new graph, or my final graph, is going to be found at, okay, I just need to do a proper graph. It's kind of hard to sketch this. So my graph then will look like this. And this is my y is equal to 3 bracket x minus 1 all squared plus 2. There's my final graph. Now, if I wanted to, I could actually expand this. How about if I expand this? Okay? And we'll make a really interesting discovery. So let's expand y is equal to 3 bracket x minus 1 all squared plus 2. I end up getting 3 bracket x squared minus 2x plus 1 plus 2. And then I end up with 3x squared minus 6x plus 3 plus 2, which ends up giving me 3x squared minus 6x plus 5. Alright, 3x squared minus 6x plus 5 is exactly the same graph as y equals 3 bracket x minus 1 all squared plus 2. All I've done is I've just expanded it, or I opened it up. Okay? But the interesting thing is that if we take a look at the y-intercept, okay, let's take a look at the y-intercept of our red graph. It goes up to 1, 2, 3, 4, 5. There's our y-intercept. The y-intercept is found at 0, 5. And lo and behold, when we have our function or our quadratics written in the ax squared plus bx plus c format, what we end up discovering is that the value of the c is your y-intercept. And taking a look, once we expanded everything, we found that the y-intercept was 5, and therefore 0, 5 was our y-intercept. Now, these are two different forms of writing a quadratic equation. One of them gives us which is the vertex form. This is our vertex form, the one that I am circling right now in black. That's our vertex form. The vertex form is useful to us in graphing because it allows us to find out what our vertex is, and it allows us to know what our translations are vertically and horizontally, as well as our vertical stretch. The advantage of having the quadratic written in the standard form, ax squared plus bx plus c, once you've expanded the vertex form, is that it tells you what the y-intercept is, something that the other form doesn't tell us. The vertex form doesn't tell me the y-intercept. And later on we'll see the importance of figuring out the y-intercept and so forth. Okay, that's basically it. I think I've talked enough for today. See you next time.